There's a crack in your foundation right now. Maybe you've seen it. Maybe you've been ignoring it. A thin line running through the mortar between two bricks, or splitting a stone clean down the middle. You tell yourself it's cosmetic. You tell yourself it's been there for years, and you're probably right. It has been there for years. But here's what most people don't understand about cracks in brick and stone. They don't stay the same size. Every winter, water finds its way inside. That water freezes. Ice expands with incredible force, enough to split rock, enough to buckle concrete, enough to slowly, quietly pull a wall apart from the inside out. And by spring, that crack is just a little bit wider than it was before. Then it happens again. And again. And over a decade, what started as a hairline becomes a gap you can fit a finger into. And then the problems that follow, water intrusion, structural shifting, crumbling mortar, those aren't cheap fixes anymore. But here's the thing nobody tells you. There's a repair material that's been sitting in your fireplace all winter. It costs almost nothing. And the people who knew how to use it built structures that are still standing after 500 years. For most of human history, there was no hardware store. There was no bag of pre-mixed mortar sitting on a shelf waiting for you. If a wall cracked, you fixed it with what you had. And what people had, for thousands of years across dozens of cultures on nearly every continent, was ash. Wood ash. The stuff left behind after the fire went cold. Now, that probably sounds like desperation, like something you'd resort to if you had absolutely nothing else. But the more you look at the historical record, the more you realize it wasn't desperation at all. It was knowledge, carefully accumulated, passed down through generations of masons, builders, and farmers who understood something about materials that we've largely forgotten. The Romans knew it. They were blending volcanic ash with lime to create a mortar so durable it's been found intact at the bottom of the ocean, still holding stone together after 2,000 years of salt water. They called the volcanic material pozzolana, named after a region near Naples, and they recognized that when certain kinds of ash were combined with lime and water, something remarkable happened. It didn't just dry, it chemically transformed. It became something closer to stone than to mud. But you didn't need to be standing next to a volcano to access this principle. Builders across medieval Europe were using wood ash in their mortars. Craftsmen in rural Asia mixed it into plasters for walls and foundations. Indigenous builders in the Americas incorporated it into their earthen construction techniques. The specific recipes varied. The underlying chemistry was the same. What made ash so valuable wasn't just that it was cheap and available, though it certainly was both. It was that ash contains silica and alumina in reactive forms. And when those compounds meet calcium hydroxide, which is what lime becomes when it's mixed with water, they don't just sit there, they react. They form calcium silicate hydrates, which is almost exactly what modern Portland cement forms when it cures. The ancient builders stumbled onto the same fundamental chemistry that engineers would later spend decades trying to replicate in a laboratory. The technique faded, the way most practical knowledge fades, not because something better replaced it, but because something cheaper and more convenient came along. Mass-produced cement arrived, and it was fast, and it was easy, and it worked well enough that nobody stopped to ask whether it worked correctly for every application. But here's where the story gets interesting. For repairing historic brick and stone, the kind of older masonry that's already cracking and crumbling around you, modern cement doesn't just fail to help. In many cases, it actively makes things worse. And understanding why that happens is the key to understanding why this old ash mix isn't just a curiosity. It's actually the right tool for the job. Think about what happens when you patch a crack in an old stone wall with modern Portland cement. It looks solid, it looks clean, it looks like it's done. And for a season, maybe two, it holds. But then something starts happening inside that wall that you can't see, and by the time you can see it, the damage is already worse than when you started. The problem is stiffness. Portland cement is extremely rigid. It sets fast and it sets hard, harder in fact than most of the historic brick and stone it gets used to repair. And that mismatch in strength is not a minor issue. It's a fundamental incompatibility that plays out every single time the temperature drops and rises. Masonry moves. That's something most people don't realize. Old brick walls, old fieldstone foundations, old limestone lintels, they're constantly expanding and contracting with heat and cold and moisture. It's microscopic movement most of the time, but it's real, and it's relentless, and it happens dozens of times a year. Traditional lime-based mortars were designed with exactly this in mind. They're slightly flexible, slightly sacrificial. When stress builds up in a wall, the mortar gives a little. It absorbs the movement. It cracks before the stone does. That's intentional. Mortar is supposed to be the weak link in the system because mortar is cheap and easy to replace. Stone is not. When you patch old masonry with Portland cement, you reverse that logic entirely. Now the patch is harder than everything around it. Now the stress has nowhere easy to go. So when the wall moves, and it will move, the crack doesn't reopen in the patch. It opens in the stone, or the brick, right along the edge of wherever the hard cement ends. You've made the repair permanent and made the surrounding material the sacrificial piece, which is exactly backwards. There's also the issue of water. Portland cement is essentially impermeable. It seals the surface completely. And in a wall that's been breathing moisture in and out for 100 years, suddenly sealing one section traps water behind it. Come winter, that water freezes, expands, and spalls the face off the original material trying to escape. This is why restoration masons are so insistent about this. Using Portland cement on historic masonry isn't a neutral choice, it's a damaging one. And the irony is that the original builders already knew exactly what to use instead. They'd been using it for centuries. They just called it something different. So what is this mix exactly? And why does something that costs almost nothing outperform a product that fills entire hardware store aisles? The base is wood ash. Specifically, the fine white ash left over after hardwood burns completely. Oak, hickory, maple, walnut. Not charcoal, not the chunky black stuff from a half-burned log. The powdery, almost silky residue that sits at the bottom of a fireplace or a wood stove after a good, hot burn. That's what you're after. And if you heat with wood, you've been throwing it away by the bucketful every winter without realizing what it was worth. Wood ash is primarily calcium carbonate and potassium carbonate. When it gets wet, it becomes mildly alkaline, almost caustic actually. And that alkalinity matters because it's what starts the chemical conversation between the ash and the other ingredients in the mix. The second component is clay. Simple, raw subsoil clay. Not the kind from a pottery supply store, though that works fine. The kind you might dig out of a garden bed or find along a creek bank where the topsoil has washed away. Clay is the binder. It's plastic when wet, rigid when dry, and it's been used in construction for literally 10,000 years. The issue people have with clay is that it shrinks when it dries and swells when it gets wet. On its own, that's a problem. But in this mix, that's actually part of the point. The third ingredient is fine sand. Sharp sand, ideally, not beach sand, which is too round and smooth to grip. The sand opens up the mix, prevents cracking during drying, and gives the finished mortar its compressive strength. And the fourth ingredient is water. Just enough to bring it together. The ratio is roughly 1 part ash, 2 parts clay, 3 parts sand, mixed with water to the consistency of thick peanut butter. That's the whole recipe. No special equipment, no curing compounds, no additives. $1's worth of materials if you're buying the sand and clay, often nothing if you have access to a wood stove and a garden. Now here's where it gets interesting. Each of those ingredients has a weakness on its own. Clay shrinks. Sand has no cohesion. Ash alone washes away. But together they compensate for each other in a way that's almost elegant. The sand prevents the clay from shrinking too, aggressively. The clay holds the sand in place. And the ash does something neither of them can do alone. It reacts slowly with moisture and carbon dioxide from the air in a process called carbonation. And over time, it converts back into calcium carbonate, into stone. Slowly, progressively, harder every season. The same process that gives ancient Roman concrete its almost supernatural longevity is working inside this $1 patch every time it rains. So now you have the recipe. The question is what to do with it. Start with the crack itself. Before you mix a single thing, the crack has to be clean. Not just visually clean, structurally clean. Take a wire brush or an old chisel and work out anything loose inside the joint. Old mortar that crumbles when you press it, plant material, dirt that's been packing in there for years. If it comes out easily, it needs to come out. What you're looking for is solid material on all sides. The patch is only as good as what it's bonding to, and if you're pressing new mortar against dust and debris, you're not patching anything. You're filling a crack with something that will fall out next spring. Once the crack is cleaned, dampen it. Not soaked, dampened. A brush dipped in water, worked into the void. This matters because dry brick and dry stone are thirsty. They'll pull the moisture out of your mix before it has time to set, and the patch will powder and shrink away from the edges. A damp surface slows that process down just enough to let the mortar do its job. Now, mix your material. 1 part ash, 2 parts clay, 3 parts sand, and water, added slowly. Work it by hand or with a trowel in a bucket. You're not looking for a pourable consistency. You want something you can press, and it holds its shape. If it slumps, add more sand and ash. If it crumbles, add a little more water. The target is that thick peanut butter consistency mentioned before. It should feel almost reluctant when you pull the trowel through it. Load a small amount onto a pointing trowel or even a flat stick and press it into the crack in layers. Don't try to fill a deep void in a single pass. Work in layers no thicker than a ½ inch at a time, pressing firmly to eliminate air pockets. Air pockets become weak spots. Give each layer a few hours before adding the next, especially in deeper repairs. Once the crack is filled flush, smooth the surface with a damp finger or the flat of the trowel. You want it sitting just slightly recessed from the face of the brick or stone, not proud of the surface. A raised patch catches water and breaks down faster. Then leave it alone. No sealing, no covering, no rushing. The mix needs air and time. In warm weather, you'll see it begin to firm within a day or two. In cooler conditions, it takes longer. And that, it turns out, is not a problem. That is exactly the point. Here is where things get genuinely interesting. Because most people, when they patch something, expect it to cure fast and stay the same. Set it, forget it, done. But this mix operates on a different logic entirely. And once you understand what's happening at a chemical level, you start to realize that winter isn't the enemy of this repair. Winter is part of the process. Let's start with what's actually happening inside the patch after you walk away. Wood ash contains significant amounts of calcium compounds, primarily calcium carbonate and calcium hydroxide. When these compounds are exposed to moisture, they begin a slow reaction with carbon dioxide in the surrounding air. That process is called carbonation, and what it produces is new calcium carbonate crystals growing inside the matrix of the patch, knitting the material together from the inside out. This isn't a fast reaction. It doesn't happen overnight. It happens over weeks and months. And crucially, it continues to happen every time the material gets wet and dries again. Every rain cycle, every frost, every thaw. Now here's the part that separates this from Portland cement. When water freezes inside a rigid, brittle patch, the kind of patch modern cement creates, it expands. That expansion has nowhere to go, so it creates microfractures. And those microfractures collect more water the next time around. And that water freezes again. And the cycle repeats until the patch falls out in chunks. You've seen it. Everyone who lives in a cold climate has seen it. The ash mix doesn't trap water the same way. It remains slightly porous and somewhat flexible at a microscopic level, particularly in its early months. Water can move through it rather than getting locked inside, and as it carbonates further through each wet-dry freeze-thaw cycle, the material actually densifies. The crystals multiply, the structure tightens, the patch gets harder. Old masons called this behavior lime-like, and they weren't wrong. Ash mortar shares real chemical kinship with traditional lime mortars, which were the dominant building material for thousands of years precisely because they behaved this way. They breathed, they moved, they got stronger with age rather than weaker. By the second or third winter, a well-applied ash patch can be genuinely difficult to distinguish from the surrounding stone, not just visually, but structurally. Run a key along it. Tap it with a coin, it rings solid. That's not luck. That's chemistry that's been understood for centuries and simply forgotten in the rush toward faster, modern solutions. So here's what I want you to do before the first hard frost hits. Go find your wood ash. Check your fireplace, your fire pit, your neighbor's burn barrel. Sift it. Mix it. Get your hands into it. Because the cracks in your walls are not waiting for spring, and neither is the water that's going to find them. This isn't a complicated process. It doesn't require special tools or expensive materials or a contractor's license. It requires attention and patience and a willingness to trust something that's older than Portland cement by about 2,000 years. The worst outcome is that you spend an afternoon outside and $1 on materials. The best outcome is that you stop a crack from becoming a collapse. Winter is the real test of any repair. Let the ash mix take that test. Mix a small batch. Patch one crack. Watch what happens over the next few months. The evidence will speak for itself.